Hey everyone! Today we are going to put everything we have seen in this chapter together and analyze a real-world dataset of average temperatures by city. Our goal is to design an API that processes data in parallel so that we can leverage modern computer architecture with multiple CPUs. For example, I'm using a laptop with 8 CPU cores, and utilizing the cloud, we can easily access computers with more than 200 cores each, should we need to. So if we want to process a large volume of data quickly, it's crucial that our algorithms fully utilize all the computing power available. So imagine we have a very large data set, maybe gigabytes or petabytes of data, and we have several CPUs available. Until now, every time we have analyzed the dataset, we have done it sequentially, which means that one CPU is in charge of iterating over the entire collection, and all the other cores are idle. This is a huge waste of resources, right? So how can we improve this situation? We need to assign some work to each core so that they are all busy. But we also want to ensure that work that each core performs is useful. For example, we wouldn't want two CPUs to process the same data. So ideally, we should separate the dataset so that each CPU is assigned to an independent section of the data. For instance, in this example, CPU 1 is in charge of partition 1 and CPU 2 is in charge of partition 2. One crucial question is how the dataset should be split. If we create partitions which are too large, then we may have fewer partitions than processors, which means that we are still wasting resources. For example, here, CPU 3 is still idle. On the other hand, if we create too many partitions, then all the cores might be busy, but our code will waste lots of cycles performing unnecessary management activities, such as dispatching tasks and loading the data. Parallelizing the work does add some overheads, and sometimes adding more CPUs actually slow down the task as a whole. This is also the reason why we don't experience a tenfold speed increase when we run a program in parallel with 10 CPUs. So it's important to balance these two concerns to achieve maximum efficiency. To make things worse, even if we carefully split the dataset, all the tasks may not require the same computing power. For example, if each green square represents a file, we could imagine that some of them could be larger than the others, which will once again impact the performance. Due to these unknowns, it's difficult to predict the performance of a distributed system. So we'll have to benchmark our implementation, and it will involve a lot of configuration specific to the task we are processing. There are some guidelines for this process, but I have to be honest with you. It will involve turning knobs until we arrive at the right settings for the task at hand. Now, the nice thing about this approach is that it scales to more than one computer. For example, instead of CPUs, we could dispatch the work to different nodes in a data center. But then we would need a distributed file system, and we would then have to worry about things like network and resiliency, because a node might break, which would mean we'll have to redo the computation somewhere else. This is a much more complex scenario that is beyond the scope of this course. However, the concept remains the same. We want to break down a collection into several parts and then dispatch them to different agents such as CPUs or nodes in a data center. This means that if we manage to leverage several CPUs locally, we would have understood the core principles behind big data frameworks such as MapReduce and Spark. And this knowledge is in high demand right now. Before we start the exercises, there is one final point that I would like to make, and it's undoubtedly the most important one. Parallelizing a computation shouldn't change the result. We are using several CPUs just to speed up the analysis, but it should arrive at precisely the same result as it would if it was running sequentially. End users shouldn't notice the difference, except that when running in parallel, it's hopefully faster, and perhaps the fans in the computer will be louder, but that's it. Okay, so let's open the file temperaturenotebook.scala. This is a Scala file we'll use to load the data, run the analysis, and print the result to the command line. The first step is to download the dataset. You will find a link at the top of the file. Then go to your favorite browser and you can download it like this. I would like to take a moment to thank the University of Dayton and Dr. Kisok for creating this dataset and permitting me to use it in this course. This file is a CSV, which stands for comma-separated values. It contains the daily average temperatures of more than 300 cities over the last 25 years, half of which are in the US. This certainly can't be classified as big data, as the file is only 134 megabytes. However, there are almost 3 million rows in this CSV, so there is certainly enough data to start experiencing performance gain when running across multiple processors. It also means we don't have to spend forever waiting for the results. So this is a good balance for an exercise. Once you have downloaded the file, you will need to move it to the resource directory of the exercises module, so that the notebook can access it easily. In our IDE, let's open the exercises module, then src, main, and resources directory, and we can drop the CSV file there. Now, to check if it worked, we can execute the code in the notebook. If you use IntelliJ, you should see a green arrow next to the class name. If you use another editor, you might need to run it via SBT in a terminal. So let's run SBT in shell mode. And on top of the notebook file, I wrote the SBT command to execute. So you can just copy-paste it and wait for the notebook to run. Eventually, you should see a message saying how many rows have been parsed successfully and how many have failed. If that's not the case, please don't hesitate to head over to Slack and ask for help in the tooling channel. Okay, so let's take a minute to review what we've done. How did we manage to run this notebook? Can we do this for any other Scala file? No, in general we can't. Normally, to run a file, it needs to contain an object, which is the case for temperature notebook. And this object must have a main method with a correct signature. However, as you can see here, temperature notebook doesn't have a main function. So why did it work? It worked because the object extends a trait app that comes from the standard library. App is a little bit magical. It adds a main function and then takes the entire code in the object, so everything within the curly brackets, and move it inside the main function, meaning that everything in this object is executed. Quite convenient, right? In Scala 3, there is another way to define a main method, and I will put an example below this video. Now let's review the existing code. First, we define a value called reader, which configures the location of the CSV file. So we say that we want to read it from the resource directory, and we specify the file name. Then we mention that this CSV file has a header, meaning that we should discard the first row. And finally, we say that we want to parse each row into a Scala case class called sample. Let's open it. So sample is a case class with 7 fields, each matching a column in the CSV. Region, such as Africa, Europe, or North America. Country, such as Algeria, Burundi, or Congo. State, which is a field specific to the US. So for half of the data, it's empty, and for the other half, it's something like Alabama, Alaska, or Arizona. Then we have three fields for the date, representing the year, the month, and the day. And finally, we have a field representing the average temperature in Fahrenheit for that particular day. So if, like me, you have no idea what the Fahrenheit is, I've also added a value that converts the temperature from Fahrenheit to Celsius. This means that you can run the analysis using whatever unit makes the most sense to you. Now let's have a look at the companion object of sample. There is an implicit define there that specifies how the mapping between the CSV row and the case class is done. In this case, it's fairly straightforward. We set that the column 0 in the CSV maps to the first field of sample, that column 1 maps to the second field, and so on. Then I use the filter method on row decoder to reject all sample with a temperature -99, because -99 is used in this dataset to represent the absence of data for that day. This is the reason why a few rows failed when we ran the notebook earlier. They all had -99 in the temperature field. Cool, so let's come back to the notebook. I wanted to mention that all the CSV parsing come from a very nice library called Kantan CSV. And if you want to have a more in-depth look, I've provided a link to the documentation here. After that, we use the method toList on Reader to actually load the data into memory. So when we parse the rows, failures can occur. For example, one row could contain a string when we expected an int. Or we could find ourselves with rows with a temperature of -99 degrees. This is why toList returns a list of either. Either is a little bit like try. It's an enumeration with two cases. One for the failure, called left, and one for the success, called right. We'll come back to either in later chapter. For now, we want to separate the failures from the successes. The most straightforward way to do this is via the method collect, which is kind of a combination of map and filter. With collect, we iterate over the list and specify what type of data we want to keep, and everything else is discarded. So we can extract the failures by keeping the left values, and do the same for the successes. So if we do it this way, we go through the entire dataset twice, once to extract the failures, and once to extract the successes. This is potentially expensive when the dataset is very large. Instead, we could have used partition map to split the collection between left and right values with one iteration. Okay, I'm almost done talking. Soon it's going to be your turn to transform the list of sample into a par list. Par list is simply a wrapper for a list of A. In other words, a list of partitions. For example, here I created a par list of int with two partitions. The first one contains numbers from 1 to 8, and the other one contains the number 9 and 10. So the first exercise is to initialize par samples in such a way that it splits the entire dataset into 10 partitions of roughly equal size. This is important because if the partitions are really imbalanced, some of the subtasks may take considerably longer than others, which means that some cores might be busy while others are idle, their task having been completed. Okay, so please pause the video and have a go. So if we check the companion object of parList, we'll see that there is a method called byPartitionSize, which takes two inputs, an int for the expected size of each partition, and a list of data. This method is in charge of splitting the input list into several partitions of the requested size. For example, if we call byPartitionSize with size equal to 3, and with a list of numbers from 1 to 10, we'll get back a par list with 4 partitions, 1 to 3, then 4, 5, 6, then 7, 8, 9, and finally 10 alone in the last partition. As you can see, each partition has 3 elements, except the last one, which may be smaller if the length of the input list is not divisible by the partition size. So it seems that this method could be appropriate to calculate power samples. But then we will need to know what is the partition size so that we end up with 10 partitions. So the straightforward way to do this is to take the current list of data, so to calculate the partition size, by taking the current list of data, look at their size, and divide it by 10, which will give us an int because it's an integer division. Then we can use the by partition size here, the constructor, to say this is the expected partition size that I want, and here is a data set that I want to split. Once we have it, once it's implemented, we can remove the lazy keyword. And to see if it works, we could write a unit test, but we could also just run it like this inside of the notebook. So we could say, okay, let's look at parse samples. We'll look at partitions. And for each partition, what we want to do is we want to print its size. It would be like a quick way to see if what we did is correct. So we could say println partition has size, and here we say partition dot size. I can never type partition correctly. Okay, so now if we print this, we'll say like partition has size something, partition has size something. The problem is that we don't know the index of the partition. So there is a method on list when you can say zipWith index that will give us access to an int on the side of when we map, which is the index of the data we are accessing. So if you do zip with index and for each, now we have a tuple here. The first one is the data, is a partition, and the second one is the index of this partition, which will make our println slightly more informative. So let's run it. So we have many partitions with size 280 to 665, and the last one has 5 elements. That's not very balanced. And actually, if we look at the number of partitions, we'll see that parse samples has 11 partitions, not 10. We see 10 here because the index starts at 0. So let's take an example to understand the problem. Say we have a list with 51 elements. 51 divided by 10 is equal to 5 because of integer division. But if we split a list of 51 elements into partitions of size 10, then we get back 5 partitions of size 10 and 1 partition of size 1. So basically, we should round up instead of down, meaning that if the division returns 5.1, we should select 6, the first integer above it. So what we can do here is to transform this int into a double in order to get like 5.1 instead of 5. Now, in the math package, there is a function called ceil for ceiling that will give us the first number above. So this will return a double, but we know that this double is an integer, so it's safe to say toInt here. Now let's try to run the notebook again. This time it worked. We can see that this time we have 10 partitions, and they have almost the same size, only the last one is slightly smaller. So it's pretty good. I'll encourage you to write a property-based test as an example to try to learn about some of the property of bipartition size. Cool. So now that we have a par list with balanced partitions, let's analyze the data. Now our objective is to find a sample with the coldest temperature in the entire dataset. As you can see, I created a method called minSampleByTemperature here. That takes a par list of sample and returns an option of sample, because a par list can be empty, in which case there is no minimum value. Okay, so the goal is to find the local minimums first, meaning that the sample with the coldest temperature within each partition. Once we have these local minimums, we'll search for the coldest sample among them. So we're not trying to parallelizing the search yet, but we are preparing the algorithm by investigating each partition separately. Okay, so please pause the video and try to implement min sample by temperature. Okay, so we want to find the local minimum first. So we'll take up our par list, we'll look at the partitions, and we'll map over it, such as we'll have then access to each partition inside of the par list. For each partition, we want to find the coldest sample in this partition. So what we can do is something very similar to what we've done in the previous lecture. We can fold left on the list and say, okay, if the list is empty, we want to return none. But because of the type inference issue that there is with fold left that we discussed before, we need to define it this way. And now here we have a function that takes B. B is the state, so it's an option of sample. And sample is the current element inside of the partition. So what we can do here is straight away pattern match on this and say, okay, in case the state is none and we get a sample, this is one option, or there is a minimum value and we processed one sample, or maybe min sample. Cool. So in the case where there is no minimum value yet, and we process a sample, it means that in this case, the sample we are processing is not going to become the new smallest sample. This should only happen for the first item we process. Then here we do have the sample with the coldest temperature and we're processing a new one. So now we need to verify if sample has a temperature colder than this one. So we can just do an if then else. We'll say if sample dot temperature Fahrenheit is lower than min sample dot temperature Fahrenheit. In this case, we want to replace it. So now in this case, sample will now become the minimum value. And otherwise, we keep the existing state, the existing min sample. Cool. So now it starts to be a bit complicated. So that's why it might be good to extract this fold inside of another function. So we could say min sample by temperature partition. So this will be per partition. And this one will basically almost take the same thing, except that it's going to be a list. And the implementation is this. And let's call this partition. So now that we have this function, we can reuse it here. It will make the code slightly more readable. Why is it grayed out? I think I probably forgot, I forgot the curly brackets. Okay, so now we see that we get a list of option of sample, meaning that for each partition, we have the local minimum for each partition. Now what we want to do is to drop all values that are none. And we can do that with the method flatten. So we can say flatten, and in this case we get a list of sample. All the nones will be removed. Now, as you can see, IntelliJ is telling me that there is a potential refactoring here. So let's have a look. It says that when you have map and flatten, you can replace it by flat map. So let's do that. Okay, so now we have a list of samples representing the sample with the coldest temperature per partitions. And now we want to find the smallest sample among this. So again, we want to do the same thing that we have done here. So we can actually call the same function again and say, or maybe this is not going to be per partition, it's going to be a min sample, we can rename it, and say this is for a list, not necessarily a partition. Cool. Does it make sense? Now, how do we test this? So there is a file called parlist_test where we'll write all the tests for today. And I wrote a unit test and a property-based test for this. So let's replace ignore by test, and let's run the entire test suite. See, so all the tests pass, so it's a good sign. Let's have a look at what we run. So here it's an example with a couple of samples, and we partition it with 3 partitions, and we verify that we got the minimum one. Here, this is a test that we have done in the previous lectures when we say, okay, let's generate a random list of samples. We split it into 3 partitions again. We call min sample, which will give us the coldest sample, and then we verify that the temperature of the coldest sample is lower than the temperature of every other sample within the list. So it's a pretty good property-based test. Now you might wonder, how did we manage to generate random samples value? This is because there is this trait, parlist test instances, where I define an arbitrary of sample. You might remember in previous lecture, arbitrary is something coming from SCADcheck that it's basically a random generator of samples. And the implementation is quite easy to read, but it's a bit tricky to implement, so that's why I've done it myself. So here, if you want, the first thing I do is to define 4 values representing the region, the country, the state, and the city. And these are all the possible values that will be used by the generator, and we use the one-off function to just randomly select one of them each time. We could have also generate a random region, a random country, and a random state all independently, but then we could end up with configuration where we have Jacksonville in Algeria, which is in the region Asia, because they will be all independent. This is one way to kind of constrain all the data to be a bit more meaningful. We don't really care here, but it makes a bit more sense. Then here I define min date and max date. This, I said that the min date is 1st of January 1975, and the max date is 1st of January 2020. And we use the choose function from Gen that will randomly select a value within these 2 dates. And finally, the same with temperature. We said that we want a temperature in Fahrenheit between -50 to 150. At least like this, it doesn't really matter, but we get some kind of sample that makes sense. We don't get something with a temperature of 900,095, which is impossible. Cool, so are there any other tests that you would wish to add for min? I'll give you a chance to pause the video and try it out. So we could add a test that shuffles or reverses the input parlist and shows that min achieves the same result. However, we can do much better than that. We can merge all the partitions of the parlist together into a single list, and then we can check that the min method on this list returns the same value as the min method on the parlist. In other words, we use list as a test oracle. Let's give it a try. So we can copy-paste this property-based test. What we want to say is min sample by temperature is consistent with list min. So we'll generate our random samples. We'll still partition it this way. Actually, we can even generate a random parlist straight away. I've created an arbitrary for this in the same file. And so what we want to do here is to convert this sample. So we want to call min sample by temperature on this. And then we want to convert this parlist into a list. So what we could do is to flatten it, kind of, to put all partitions one after another. So let's say samples list. And this one will say partition. So this will give us a list of partition. And we can use the method flatten on this. So then what we want to do is to say, okay, min sample by temperature should be equal to the sample list. And here we'll use min by option. So min by option, we need to provide a function from sample to something within a sample that will be used to order it. So here we can say, I want to use min by, and I want to use the temperature Fahrenheit as the point that we use for comparison. Now we can assert that, I must have made a typo. We want to assert that finding the mean via the custom method we did for min sample, or finding the mean via the list API is going to return the same thing. So let's run the test. Nice, it works. So one thing we can do here is actually This method seems to be quite convenient, to take a par list and convert it into a list. So we could maybe extract it and define it on the sample class. To say, for example, a toList that will return a list of A, and it's just going to be a partition flatten, which means that then in our test we can simply say samples.toList. Let's rerun the test to see if we haven't broken anything. All good. So I really like this usage of a test oracle here. It sometimes feels like cheating because the technique requires a reliable implementation of the function we are testing. So this often raises the question, why do we need a new implementation? However, this is different here because parList is a much more complex data structure than list. But it's easy enough to merge all the partitions of a parList into a list, as we did it here with the method toList. Test oracles are extremely useful way to ensure that our parallel algorithms produces the same result as a sequential one, which is a fundamental requirement when running a computation in parallel. So now that we have implemented min sample by temperature, let's find out which sample is the coldest in our dataset. So let's go back to the notebook, and what we could do is just write a println here and say the coldest sample is coldest sample. We can even remove the lazy value. And here I want to run the notebook. Let's see what it gives. Unsurprisingly, it's Alaska in 1999, where it seemed that they experienced a temperature of -50 Fahrenheit, which is equivalent to -45 Celsius. Now let's move on to the next question, where we'll try to compute the average temperature across the entire dataset. I've prepared a few slides to illustrate how to calculate this. First, we'll calculate the sum of the temperatures for all samples in partition 1. And we'll repeat this operation for partition 2 and 3, which will give us 3 numbers representing the sum for each partition. Then we'll add up these numbers to obtain the total temperature across the entire dataset. This is exactly the same strategy that we use to compute the mean temperature. Then we'll repeat the same process to calculate the size of the dataset. First, we'll compute the size of each partition, and then we'll sum up each intermediate result to obtain the total size of the dataset. Then, once we have the total temperature and the size, we can calculate the average by dividing the total temperature by the size. The only thing to keep in mind is that in case the parList is empty, we want to return none. Are you ready? Okay, so let's pause this video and give it a try. Okay, so we want to calculate the sum, the total temperature. So say a sum temperature is going to be a function, it's going to be a helper function that has almost the same signature. It takes a parList of samples, but it returns a double. In this case, we can return 0 if the parList is empty. And we also need to calculate the size. So the size will say, if you give me a parList of sample, I will return an int, right? Now we know that once we implement these two helper methods, the average temperature will be fairly easy to calculate. So we can say val total equals sum temperature samples. Then we can say length, it's equal to size of sample. And then we just want to say if length is equal to 0, and in this case we'll return none. Otherwise, we'll return sum of total, maybe total temperature to make it a bit more meaningful, total temperature divided by the length, right? So really the important part is implementing some temperature and size. So how do we implement some temperature? We want to take our par list of samples, iterate over each partition. So we'll do a map here, partition map, which will give us access to each partition. Then within each partition, we want to sum the temperatures. So what we can do is, the standard thing, to do a fold left. We say, okay, the default value is 0.0. There is like no temperature. And we want to sum up. So this here we have the B is our accumulator. So this is the state. And here is a sample. So what do we want to do? We want to say state plus a sample dot temperature Fahrenheit. This will give us a list of double, like a list of the sum temperature per partition, and we want to sum these values. So we can again do a fold left with 0.0, but this time the combined function will simply be plus. We can slightly simplify this implementation, because whenever you do like a fold left with 0 and sum, there is a function .sum on list. And we could also simplify this one. It would be a bit less efficient, but much more readable. We could say map dot temperature Fahrenheit sum. So for the moment, we favor, like readability over efficiency, and we'll look at it later. So you see here, sum temperature, we map over each partition. For each partition, we calculate this, we look at the temperature, we sum it, and then we sum everything together. For the size, it's going to be very similar. We take the samples, we map it. For each, sorry, not map on samples, but map on each partition. For each partition, what we want to do is to calculate its size. So we can say underscore dot size, which will give us a list of int. And again, we can use sum to sum these numbers together. Okay, so let's have a look at our test, our unit test, to see if it works. So here we can remove the ignore keyword. And here I just created like a few test examples, and we expect this value at the end. And the test pass. Now what about property-based testing? Please pause the video and write one for average. Okay, so it's not really easy, but I found this example quite interesting. So let's start. Say average PBT. We don't really know yet what we want to do, and we want to generate a par list of samples. So we'll say samples. It's a par list of type sample. We know that we somehow want to call average temperature on this. Now what can we say on this number? Well, the average has a very nice property, is that if you multiply the things you are averaging by a certain number, let's say you multiply it by 2, then it will also multiply the average by 2. Think about it. If the average price is 100, you multiply the prices by 2, you will get 200 for average price. This is the same for temperature. So what we could say is that let's iterate over all the samples in the par list, let's multiply the temperature by 2, and let's verify that the result of the average is twice bigger. So this means that we need a method to update every element in a par list, but this should be quite easy to write. We could say, okay, map. It's a higher order function that takes a function from A to 2 as an input. So this will be the update that we apply on every element. And this will return a par list of 2. So now the implementation of this is we create a new par list where we take the existing partition, we map it. This gives us access of a partition inside it. And what do we want to do for each partition? We want to apply the update function. That's it. If we want to make it slightly shorter, we could use an underscore here, but it may not be more readable, so I'll not do this. Okay, so now what we do is here, average temperature, it gives us an option of double. So let's pattern match on this to consider the two cases. If it's a none, what can we say about this? So if it's a none, the only thing we could check is that the parlist of sample is empty. So we could say assert samples is empty. So we could say toList is empty. Or we could even write a method isEmpty on parlist. I'll let you do that as an exercise. Here, this is like AVG, the average. So this is where we want to calculate the average again, but this time on the samples where, okay, maybe let me extract it. So this will be new samples. The new samples are going to be the current samples where we map it. And for each sample value, what we want to do is to call the method copy on it. Because sample is a case class, so every single case class has a method copy. It's implemented by the compiler for free. And this method allows you to specify what you want to change. So you can change several fields at once, but here we only want to change the temperature. So we say temperature Fahrenheit equal the current temperature in Fahrenheit times 2. And every other field will stay the same. Okay, so this will be our new samples with the temperature twice bigger. We want to call average temperature on these new samples. This will again give us an option, so we can again pattern match on this. This time, if it's a none, then it should be an error, because we were in a case where the average was not empty, so that there were some data. If now we get none, it means that we somehow screwed up when we implemented map. So we can say something, maybe not an assert, we can just say fail, problem with map, I mean, or better error message. But the thing is that here the problem will be with map, not with average. Or very, very likely this way at least. Now this will be the average 2. And what we want to verify here is that average times 2 should be equal to average 2. Right? Let's run the test. It works. One thing, that is a bit dangerous with doubles is, when you transform doubles, you always have the risks that there will be rounding errors. So another thing, like it seems to work now, but maybe this test will fail after a while since we are generating random numbers. One thing you may want to do is to calculate the difference between AVG times 2 and AVG 2. And you want to say the absolute value of this. So you want to know the difference between these two values. And you want to say this should be lower than some kind of very, very small double. So this is a hacky way to say, okay, I know that this number should be equals, but because doubles precision, you can always have some issues. Here it's a way to say, okay, I allow this kind of difference. There are also other ways to do this via Scala test to say, like, I want to compare two numbers with allowing some kind of difference. So let's run the test to see if it still works. Yeah, it seems to be good. Another test we could have done, which is very similar, is to say that we take the average and we remove this average from every single number inside of the samples. So instead of multiplying by 2, we could have said minus average. And then in this case, the second average should have been equal to 0. Because this is a definition of, if you have an average of several numbers that is equal to 10, you do minus 10 to every single number, then you move back the average, you recenter it around 0. But the idea is the same. Cool, isn't it? Cool. So now that we have a way to calculate the average temperature across our data set, let's have a look at what is the actual average for our example. So we can remove the lazy value here, copy-paste the println, and say that the average temperature is average temperature. And let's rerun our notebook. It will take some time because you have lots of data to load into memory, but eventually we should get a response. So as we can see, the average is equal to 60.37 something, which in Fahrenheit, which is equivalent to 15 degrees Celsius. A bit cold, but not freezing. So the next step is to go back to average And now we're going to try to improve the performance of this function. Currently, we are iterating twice over the collection. Once to calculate the sum of the temperature, and another time to calculate the size of the dataset. Instead, we could calculate the sum and the size in one go. For example, we could go through partition 1 and calculate the total temperature of its samples, as well as the size of the partition. Then we do the same for partition 2 and 3. This way we obtain 3 tuples, one for each partition. And finally we add them together, which will give us the total temperature and the size for the entire dataset. So please pause the video and try to refactor the average function using the algorithm I've just described. Okay, so we want to calculate the total temperature and the length in one go. So how are we going to do this? We'll first need to iterate over each partition, as we have done before. So .map partition here. Now the main difference is that the way we fold each partition, now it's going to be a bit more complex. So maybe let's annotate the type of fold left, the expected type, to make things a little bit clearer. So eventually what we want to get here is a tuple that is both a double and an int. The double will represent the sum, and int will represent the size. So the default value, this is what we're going to return in case the partition is empty, which means the temperature will be 0 and the size will be 0. Now here it's our combined function. So the combined function takes 2 arguments. The first one is a tuple, which represents the sum, temperature, and the size we have seen so far, the state, if you want. And the second argument is a sample we are currently processing. So we can pattern match on that to make the code slightly more readable. So we can say sum, size, and sample. I don't know why it put type. It's not required. Okay. And what we want to return is a new tuple after processing this sample. So it's going to be sum plus sample.temperature Fahrenheit. And the size is simply going to be size plus 1. This is what happens if you process one item. Now the code starts to be a bit complicated, so it might make sense to extract it in a separate method. So we might want to say sum size per partition. And this is going to take sample or partition that is a list of sample, not a par list, and return a tuple double int. It's not necessary, but I think it will make the code clearer eventually. So we can just extract this code, move it here, and then we can use this function inside of IntelliJ. Now, the return type of this expression, so maybe we can give it, you can ask IntelliJ to show the type. Now, it's a list of double int. But what we want to get is a tuple double and int. So it means that we need to, again, fold each intermediate result into a single tuple. Again, maybe let's write a function that does this. So maybe it's going to be some tuples that will take this type. So this is going to be the tuples. And we want to get a single one out of this. Right? How do we implement it? So we set tuples, fold left. Now the default value is going to be the same as for some size partition, is 0.00. This is the default value in case there is no partition, the part is completely empty. And here the combined function is a bit tricky. So if we look at the type, it says that it takes 2 arguments. The first one is b. b is the type of this. So maybe let's annotate it to make it, again, more clear. Now we'll see the type of this. So it takes 2 arguments. The first one is a tuple double int. The second one is a tuple double int, which makes sense because this is a state and this is a current tuple that we are processing. So when we pattern match, we can say sum1, size1, then sum2, size2. And what we want to do eventually is to do sum1 plus sum2, size1 plus size2. Not very beautiful, but you know, it does the job. Okay, so now that we have this function, we can call it on this, and this will return a single tuple. So we could define here, I don't know if I've shown you this syntax, but because this returns a tuple, we can kind of straight away pattern match on a tuple this way. So this will mean, here we are folding the sample in one go, then we are folding each partition, then once we have our list of intermediate results, we fold all the tuples together. This will give us a single tuple, and we reuse it, we pattern match on it straight away. So let's run the test, because we wrote tests for average temperature. So now if we run the test, we'll see if we broke anything. Oh, actually, I run the wrong one, because this is a notebook. Let me change it. Let's run the test now. All good. It was pretty tedious, but we did it. I strongly recommend extracting each fold into a separate method, as we did here, because it makes the code more readable, because we clearly see the input and output types. This is generally a good pattern to follow whenever the code becomes too nested or complex. Okay, so we have seen with mean and average that it is possible to calculate intermediate results per partition and then aggregate those results into a single value. Now let's try to capture this pattern using a single higher order function. This will allow us to reduce code duplication, as we can rewrite mean and average using this method. But most importantly, if we manage to make this new method run in parallel, we'll get a parallel version of mean and average, essentially for free. We don't know if it is possible, but if it does work, it will save us lots of time and effort. Okay, let's visualize how it is going to work. We start with a dataset split into 3 partitions. Then, we define a default value, and we start by folding the first partition using a combined function. For mean temperature, we'll check which sample is the coldest, and for size, we simply use +1. When the first partition is completely consumed, we obtain an intermediate result. Then, we repeat the same process for partition 2 and the same for partition 3. In the next step, we fold all the intermediate results using the same default value and combined function that we use for the partitions. Finally, once all the intermediate results are processed, we obtain the final result. Does that make sense? Okay, if so, let's go back to the temperature exercises file, where we'll try to implement fold left for parlist, so that it works exactly as the algorithm I just described. Once you're done, you can move fold left into the class parlist, which will make the API more user-friendly. So please pause the video and try it out. Okay, so let's go. So the code is going to be very similar to what we've done before, because we're just trying to generalize the same pattern. So we'll take the parlist, we'll iterate over each partition. So this will give us access to each partition. For each partition, we want to fold it. We want to fold it. The default value we use here is the variable default. The combined function is going to be this combined function that we have as an input. Then this will give us a list of 2, so a list of intermediate results. We want to fold it again. So we'll again do fold left here, using the same default value and the same combined function. Fairly simple, right? Especially once we have already done it. Except that, as you can see, IntelliJ tells me that here it doesn't work. So it says that This is because when we try to fold the intermediate results together, we need a combined function that takes a pair of 2 and returns a value of type 2, which doesn't match the combined function that we have, which takes a 2 and a from and return a 2. So let's go back to the diagram to see what happened. When we fold each partition, we need a combined function that takes a value of type 2, the type of the state, which is in blue here, and a value of type from, the type of the data inside the partition, which is in green in the diagram. However, once we have computed all the intermediate results, we obtain a list of type 2, right? This means that when we fold all the intermediate results together, we need a different combined function, one that accepts 2 values in blue or 2 values of type 2. Okay, so that's a bit of a setback, but it's also a good example of how to use generic functions to design an API. When we implemented mean and average, we didn't notice that we needed 2 different combined functions. At least I didn't notice the first time I went through these exercises. However, once we introduced the type parameters, it quickly became obvious that it is impossible to implement fold left on parlist, at least not with this signature. Okay, so I think this is a good place to take a break. This will give you some time to think about how would you solve this problem on your own. So I'll see you soon for the next video. Bye! Don't forget to check out my website, fp-tower.com, to get access to all my functional programming content and sign up for my course. See you soon!